This video is to help you with your review problems for sections 5.1 to 5.4 for the quiz tomorrow. 1 and 2, I'm assuming you can follow. If you have any trouble with those, just please come see me tomorrow morning and we can talk about them, but I think you're probably okay with those. So we're going to begin with number 3. 3 men and 3 women available to fill 2 identical seats on a committee, and Y is the number of women chosen to fill those seats. So find the mean and variance. Okay, so I'm going to switch over to the solutions and just sort of walk through them with you. Okay, so here's number 3 at the top of the screen. I'm using a little lowercase y to distinguish or to denote the possible values of our random variable uppercase y. And so we can have 0, 1, or 2 women on the committee. And as you can see, I've just created this table where I have y squared available to us so that we can use that to find the variance later on. But our probability distribution is such that we're thinking about the fact that we're trying to pick 2 people out of 6, and so our denominator is 6 choose 2. And then in the numerator, we have 2 factors. The first is how many men we're choosing, and then how many women we're choosing. So we have in the first row here where we're choosing the first factor is how many women we're choosing, the second factor is how many men we're choosing. So in the first row where we have choosing 0 women, we have 3 choose 0 times 3 choose 2 for the men out of a possible 6 choose 2 in the committee, and that's 3/15. When we're choosing 1 woman, we have 3 women choose 1 woman times 3 men choose 1 man out of 6 choose 2, and then for y equals 2, 3 women choose 2, 3 men choose 0 out of 6 choose 2. And you can see the fractions we get, right? And you can verify that they add up to 1. Remember, that's always a good idea to make sure that your probability distribution is correct. If that adds up to 1, you've probably done that correctly. And then, of course, we've got in the next column of the table, the y values times their probabilities, so 0, 9/15 and 6/15 respectively. And then in the final column, y squared times their probabilities, and you can see those values there as well. Remember, the expected value is just the sum of the column that contains the values of y times the probability. So we get 6/15 plus 9/15, which is 1. So over time, right, remember what the expected value means. It means that over time, or over a number of iterations of this experiment, we would expect on average there to be 1 woman exactly on average out of the 2 committee members, which makes sense if you have an identical number of males and females, right? So, and then the expected value of x squared, or of y squared, I guess I should say, is the sum of y squared times the probability values, right? It's not just the mean squared. So be careful about that. We'll talk more about that in a future problem on one of the future videos here in number 7. But the expected value of y squared is 21/15, which of course works out to 7/5, which you can see there. Okay, so in part A, the expected value is 1. In part B, remember our formula for the variance. We've got the square of the expected value of the variable squared minus the square of the expected value of the variable. So 7/5 minus 1, of course, is 2/5. Just to elaborate on the reason that the expected value of the square of the variable is different, and in this case larger than the expected value of the variables squared. So in this case, the expected value of our variable is 1. The square of that would obviously be 1. The expected value of the square of our variable is 7/5, obviously greater than 1. If you think about why that is, I want you to look at the table and notice that 0 and 2 as values for our variable are equally likely. Both 3/15 or 1/5. And that the only other value is 1, which happens to be the expected value, right? And that's, of course, 3/5. So think about what happens when you square. When you square these values, right? 0 squared is just 0, but 2 squared is 4, right? So the square of that value, as the values increase, lend more weight to the probability that is associated with them, right? So, 0 times 3/15 is still 0, just like 0 times 3/15 was 0 when it was just the value itself. But now, when we square that variable and we're taking 4 times 3/15, well, the larger value is lending more weight than the smaller value did previously. And so naturally, the expected value of the square of the variable is going to be larger than the expected value of the variable itself. So hopefully that makes sense. Again, we'll look at that again in problem 7.